far, we've seen lots of examples of how to compute indefinite integrals with integration by parts. What I want to explain in this last video is how things change when you compute a definite integral with integration by parts. That is, how do things change when your integral has endpoints? So as the starting point, remember, integration by parts says that you start with two functions of x, u of x and v of x, so that the function you're trying to integrate can be written as the integral of u dv. And that's equal to u of x times v of x minus the integral of v du. So what changes when you have endpoints? So integration by parts with endpoints. It's the same setup where you now have the integral of a function from a to b that you can write as u dv. You still get u v minus the integral of v du. But what you want on the right-hand side now is a number. So what happens is this integral of v du also goes from a to b. And the function u times v, we evaluate at b and subtract the evaluation at a, just like in FTC2. So this is the big formula to remember. What happens when you have endpoints, when you're doing a definite integral, is you have an integral from a to b. You have uv evaluated at b minus the evaluation at a, and minus the integral of v du between the same endpoints, which, if you had to take a guess at what happened, this is exactly what you would expect, because this is how we know how to get a number out of a function with some endpoints. So in the rest of this video, I just want to give some examples. So let me start with the integral from 1 to e of natural log of x squared dx. OK, so we need to pick something to be u and something to be dv. So we need a function that gets simpler when we differentiate, and then something that doesn't get that much worse when we take an antiderivative. And what we're going to do is use something from the previous video. So if you let u be natural log of x du, it's 1 over x dx, and everything else in this integral should be dv. So dv is also natural log of x, but now dx. And that means that v is an antiderivative of natural log of x, which we saw in the last video is x natural log of x minus x. So this integral is now equal to uv, so ln x times x ln x minus x. This function evaluated at 1 and at e. Let me make this a little easier to read. Equals evaluated at 1 and at e minus the integral of v du, x natural log of x minus x, all times 1 over x dx, evaluated at 1 and e. Why does this work well? Well, when you evaluate at e, this top function, natural log of e is 1. E times natural log of e minus x minus e. This is ln e is 1 times e ln e minus e. This is e times 1 minus e. So this is 0. This is 0. And now when we subtract the evaluation at 1, we get ln of 1 times 1 ln 1 minus 1. And ln of 1 is 0. So this is also 0. So this whole term is 0. So this integral is equal to just this minus integral 1e x ln of x times 1 over x. Let's rewrite this. This is ln of x minus 1 dx. And now this is an integral we know how to do because we know antiderivative of natural log of x from the previous video. So I'll pause and rewrite this up at the top with more space and show you the rest of this integral. Our goal is to compute this integral at the bottom, negative integral from 1 to e of natural log of x minus 1 dx. I've rewritten it larger up here. We can rewrite this integral of a sum of two functions as the sum of the integrals. We have minus integral from 1 to e of natural log of x dx plus this minus 1 cancels with this minus 1 plus the integral from 1 to e of 1 dx. This first integral, we know an antiderivative of the function natural log of x is x natural log of x minus x. So I'm going to keep this minus sign outside the whole thing and evaluate this function x natural log of x minus x at e end at 1 using FTC2. And then this second integral is the integral of a constant function. So we get c times b minus a, where c is 1 and b minus a is e minus 1. We evaluate now x ln of x minus x evaluated at e as e natural log of e minus e. Natural log of e is 1. So this is e minus e is 0. And we subtract the evaluation at 1. We get 1 times natural log of 1 minus 1. Natural log of 1 is 0. So we're just left with minus 1, a plus 1 in here, and there's a minus 1 outside. So we get minus 1 plus e minus 1, which is e minus 2. So this is an example that where you have to do integration by parts. And in order to make the integration by parts work, you need to use this result from the last video about the antiderivative or the indefinite integral of natural log of x. So you should think of adding this integral of natural log of x to your toolbox of integrals that you know, so that if you want to set like dv to be equal to natural log of x dx, that's fine now because we know an antiderivative of natural log of x. So I'm going to pause and erase and then give one more example of integration by parts where you have a definite integral. So what happens when you have endpoints? The last example that we'll talk about is a little bit different than anything we've done before. Suppose that f is some function where f of 2 is equal to 3, and the integral from 0 to 2 of f of x dx equals 5. Our goal is to figure out the integral from 0 to 2 of the function x times f prime of x. So in every other example we've done so far, if you're taking the integral of a function x, f of x, we tell you what the function f of x is. Here, you don't know what this function is. You're just given some partial information about it. And then you're not asked to compute the integral of the function f. You're asked to compute the integral of some function that's related to f in some way. So this feels very odd. But this kind of problem works great with integration by parts. So the idea is, OK, we want to set something in x f prime of x dx equal to u, and the rest to be equal to dv. We want the u piece to get simpler when you differentiate. And the dv piece, we want to not get much worse when we take an antiderivative. Well, we don't know anything really about the function f prime of x. But we do know some stuff about the function f of x. So that's a good hint that you should set dv to be equal to f prime of x dx, because then v you can let be equal to f of x. So then if you make that choice, u has to be equal to x. And this is nice because it gets simpler when you differentiate. So where does this leave us? So the integral from 0 to 2 of x f prime of x dx is equal to uv x f of x evaluated at 0 and 2 minus the integral from 0 to 2 of v du of f of x dx. Let's just say what this means. So this is 2 times f of 2 minus 0 times f of 0 minus integral from 0 to 2 f of x dx. 2 times f of 2. F of 2 is one of the pieces of information we're given at the start of this problem. So this is 6. F of 0 is not given to us. We have no idea what f of 0 is equal to. It could be 1,000,000. It could be negative pi. But it doesn't matter because we're multiplying it by 0. So this piece gives a 0. And then we have minus this integral from 0 to 2 of f of x dx. And that is the other piece of information we're given at the beginning of this problem. So what we get is 6 minus 5 is equal to 1. So what's kind of amazing here is that there are many, many, many different functions that satisfy f of 2 equals 3 and the integral from 0 to 2 of f of x dx equals 5. But all of them give the same value of the integral from 0 to 2 of x times f prime of x dx. So this is one other type of problem to be aware of. When you see a problem with this kind of partial information, that's a really good hint that applying integration by parts is the right idea. And how do you know what function to let be equal to u and what you want dv to be? Well, you want to make it so that when you go from dv up to v, you get a function where you actually have more information.